Okay, let's do a kinematics summary. The first thing we want to do is talk about some vocab words. So we discussed distance, displacement, and position. And they're all similar. We use them, and in real life we kind of interchange them sometimes. But distance is really the total path length, right? It's the total accumulation of all of your steps, no matter what the direction is. It's a scalar, which means it only has magnitude, which means it only has a size. Displacement is your change in your position, right? A delta x. Delta means the change in. X final minus x initial. It's a vector, which means it has magnitude and direction. A very simple example would be if I walked 3 steps this way and then 4 steps that way. If I did something like that, right? The distance I traveled was 7, but my displacement is actually going to be this dotted line. It's the difference between where I started and where I ended, and so my displacement is actually 5, at a certain angle. So they are much different. Those two things are big time different. Your position is really just your location. It's usually given as a function. And in physics, we don't always do x of t. That's kind of like math notation. We just say x. So if you see like x equals, that's a position function. Speed is how fast you're moving, right? If you're explaining that to a 10-year-old, it's literally just how fast something is moving. The units, of course, all of these are in meters. And when we start talking about speed and velocity, we're talking about meters per second. But it's the magnitude of velocity. You might think that says absolute value of the velocity vector, but it's really the magnitude of the velocity vector. It's the size, and it is a scalar. Where velocity is a vector, which means it is both speed and direction. This is really kind of the next unit, but this is the velocity vector given in components form. This would be like how fast it's moving horizontally, and this is how fast it's moving vertically. Together, they form the speed and the direction, or you could say the velocity vector is 30 meters per second at some angle, right? Like 20 degrees north of east, or 20 degrees above the x-axis. Velocity is the rate of change of position versus time, which means the velocity is the derivative of your position function. This is more of a calculus point of view. It's the instantaneous velocity. It's the velocity at a single moment in time, where average velocity is over some time interval. It's how much you've changed your position, your displacement, over a time interval, which is really an algebra viewpoint. If I talked to you about a positive velocity, well, positive velocity is a positive rate of change of your position, which means you're moving to the right? You're increasing your position. A negative velocity is moving left. That's not really telling you whether you're going away or towards the origin, but if you tell me you have a positive velocity, you're increasing your position, you're moving right. Negative velocity, you're moving left. An example, a 4 meter per second velocity means you're increasing your position by 4 meters every second. Okay, next word is acceleration. Acceleration is also a vector. It's the rate of change of velocity versus time. So A is the derivative of velocity. That's an instantaneous point of view. That's the calculus point of view. And then, of course, we can do an average. Average acceleration is delta V over some delta T. That was supposed to be delta T there. An acceleration might be like 3 meters per second squared. It's probably better viewed as saying it's 3 meters per second, right? If you say you have a positive 3 acceleration, that means you're increasing your velocity by 3 meters per second every second. So every second, you're increasing your velocity. That does not mean you're speeding up, because if you were going a negative velocity, positive acceleration would increase the velocity and actually become less negative. So you got to be really careful about speeding up. But for sure, positive acceleration means an increasing velocity, just like a positive velocity means an increasing position. Positive velocity, moving to the right. Positive acceleration, increasing velocity. It doesn't tell you the direction, and it doesn't even tell you speeding up. It tells you exactly what it's supposed to say. A positive acceleration is a positive rate of change of velocity, which means your velocity is increasing, not necessarily your speed. Okay, from a graphical point of view, right? We can look at very easy position graphs, which you would have looked at in Algebra 1 or even in honors physical science or something. An x versus t graph is showing your position, right? This is literally your location at the beginning, and this is your location 2 seconds later. What we know is that the slope on this graph, right, the rate of change of position is velocity. Again, the rate at which the slope is changing, well, that's a changing of a velocity. Well, that's acceleration, right? We talk about the curvature on a graph. If you had an x versus t graph, and it was linear, meaning there was no curvature, if this slope is constant, that means the velocity is constant, which means the acceleration is 0 because there's no curvature. There's no changing of a slope. Again, when you're looking at this graph, the y values, of course, are just your horizontal position. The slope is your velocity, and the way the slope is changing is acceleration. In this case, the slope isn't changing, which means there's no acceleration, and it means a constant velocity. In this case, it's a constant positive velocity, which means you're moving to the right. As you can see, as you move along the graph, your x is increasing. Okay, now if we have a velocity versus time graph, well, now the slope is the rate of change of velocity, which we've defined as acceleration. The area under the curve, meaning this area here, the accumulation of velocity over a time period, right? If you accumulate velocity, meters per second, over a time period, you get a change in position, right? Delta x. So the area here represents delta x. This is the integral symbol or the antiderivative symbol. It says that the change of position is the accumulation, the sum up. That's really a summing function of the velocity over some time period. And you could say it like this in some calculus symbols. If we have an acceleration versus time graph, well, then the area is a change in velocity. Again, we know that this area here is some positive. Let's say the area is 10. We have no idea what direction we're moving. We don't know if we're speeding up or slowing down. All we know is that in that time period, we increased our velocity by 10. Right? The area is the change in velocity. Since the area is positive, we know it's a positive change, and that's it. This is the change in velocity. It's some accumulation of acceleration, right? If you accelerate over a time period, you've increased or decreased your velocity. Okay, let's flip then. Okay, all right, now we went to the big three. The big three, so this is our position function, right? This is our position function. Of course, that's our velocity function. And then they call this like the v squared equation. Okay, our position function can tell us where we're located if we know initial position, initial velocity, and an acceleration, and for how long we accelerated. I put plus or minuses here just to remind you that the velocity and acceleration are vectors. So if we were, running to the left, or we threw something down, we're going to use a negative here. If our acceleration is in the opposite direction of our velocity, right? If our velocity is to the right, but we're accelerating left, in that case, that would be slowing down, or we're going to use a negative sign here. I think it's pretty obvious in the story what these signs should be. Again, if you're braking, your initial velocity is going to be bigger, so you're going to have to subtract AT. But there's our velocity equation. There's our v squared equation. Remember, the v squared equation was created by just taking the velocity equation and solving for time and substituting it into the position equation. And if you manipulate that all down, you get this equation. It didn't come out of thin air. This x is really a delta x. It's really, typically, it's the distance associated with the acceleration. So if you accelerated for 50 meters, or you had 30 meters to stop, that's that distance right there. Lots of times we don't really change direction. So in this particular example, whether you call it a displacement or a distance, it's typically going to be the same. It really is a delta x though. These equations all morph into this if we have free fall. Free fall is just a specific example of constant acceleration. The acceleration just happens to be g. G is the acceleration due to gravity, and on Earth it's 9.8 meters per second squared, which means we're going to accelerate towards the Earth at a rate of 9.8 meters per second every second. So if I drop a ball or I drop a feather, we're in free fall, meaning there's no drag, right? No drag forces. And then the only thing we know is that we're going to, in that case, we're going to, our velocity is going to go more down at 9.8 meters per second every second. Typically, we're talking about speeding up, but if we threw something up, well, then gravity, of course, is going to slow it down until it stops, and then it's going to speed it up back on the way down. So these equations then just get changed to minus g's. And then this is really a plus or minus, because if I throw something up, then gravity is going to slow it down, so it's going to be a minus sign. If I happen to throw something down, gravity is going to speed it up, and so then it would be a plus. That h, again, is really a delta h. You know, it's not the height of something. You know, if I took something on a building and I threw it up, and I wanted to know how high it would go, this h is associated with the acceleration. That h would only be that. You would, if you wanted to know how high it actually went, you would have to add the initial h into that equation. Okay, so what if the acceleration isn't constant? Well, if the acceleration isn't constant, we can't use the big three anymore. The big three are only based on constant accelerations. Okay, so if it's not constant, well, then we have to use calculus. And really, we can use calculus all the time. If you take the derivative of this position function, you do get this. If you take the derivative of this, you get a constant acceleration, which proves the fact that that's what it's useful for. But just as a reminder, velocity is the derivative of position. Acceleration is the derivative of velocity, right? Velocity is the rate at which you change your position, a rate, a slope, a derivative. Acceleration is the rate at which you change your velocity, the derivative of velocity. For polynomials, meaning things that look like this, we use the power rule. The power rule says, down here I think I have it, that for the derivative power rule, you're going to bring the power down and decrease the power by 1. So I'm going to bring the 3 down to make it a 15 and decrease it to a square. Bring the 2 down to make it 20 and decrease. The derivative of a constant is 0. I mean, what's the rate of change of a constant? Well, nothing. That should make sense. And then I can take the derivative of velocity to get acceleration. Okay? Graphically, right, the differences between an average slope and an instantaneous slope is this dotted line. If I'm looking at this position versus this position, the dotted line is the average slope, so it's the average velocity, where this is the instantaneous velocity at that moment. Right? The difference between algebra and calculus. Calculus looks at an instantaneous rate of change. Algebra looks at an average rate of change. The units are really important in the dimensions. Certainly the units of position is meters. Velocity should be in meters per second. Accelerations are in meters per second squared, or meters per second. Remember, that's what an acceleration is. It's changing a velocity over time. The integral power rule is a little more complicated, but it is just the reverse. You increase the power by 1 and divide by the new power. The thing you have to be careful of is when you're integrating, you have to be careful of initial positions. And what I mean by that, if you just know the velocity is 4 plus 2t, if you integrate and you increase the power by 1, make that a 4t, and make that a t squared, what you don't know is that initial position x. But if you had initial conditions and you knew that, that would give you the ability to find out what that constant was. You won't know that constant by looking at this equation, because it would have went away. And again, in class, I'm sure we would have went in depth on the power rule. So power rule, units, graphs, derivatives, the big three version is free fall, and then all the vocab words we used at the beginning. Hopefully this is a pretty good review of kinematics. I will put this sheet on there as well as notes.